In this video, we will continue our look at limits at infinity. Previously, we looked at these limits via a numerical approach using tables or a graphical approach, and then we are now going to see how we can use algebra to gain the same information regarding these limits at infinity. Now, the method that's used algebraically depends heavily on the type of function. Specifically, it depends on what type of elementary function we're taking a limit at infinity of, and then based on that, there is a particular procedure. So what we will do in this video, and actually the next video, is walk through the different types of functions and talk about their properties with regarding to these limits at infinity. Right? So let's start with probably the simplest type of functions, polynomials. Right? And remember, for instance, linear functions are just a special case of polynomials. They're polynomials with degree 1. And in each case, what I'm going to do is write down the general form of the function and then highlight any key definitions that we need to keep in mind, which may affect how we evaluate these special kinds of limits. Now remember, a polynomial is a function of this form, right? So you have powers of x, right? And in a second I'll say what type of powers are allowed, and then you're multiplying those powers of x by coefficients, and then technically it can go down to just a constant, right? And the assumption here is, so if a sub n is not 0, so if your leading coefficient is not 0, then the degree is n. So the degree is equal to n. And what is n? N is a non-negative integer, right? So it could be 0 or 1 or 2 and so forth. So n, a non-negative integer, right? So what that is saying, you can't have a polynomial, for instance, where your power of x is a fraction, or it can't be negative, or it can't be an irrational number. It has to be either 0, which would be a constant polynomial, or it has to be positive, and then you'll get a linear polynomial, a quadratic polynomial, etc. Right? Let's see what else. So yeah, that's pretty much all we need here to talk about these. So the question is, and what I will do is illustrate this with some examples, right? So let's look at some examples of this. Now remember, with limits at infinity, your x is going to either plus or minus infinity. So let's take a simple one. Let's say we're going to compute the limit as x goes to infinity, and then my polynomial is like 2x squared minus x plus 1. Right? So the thing about polynomials, the important term that we want to highlight is that leading term. So it's this term here that is relevant as far as limits at plus or minus infinity, right? So this is sometimes referred to, again, I'm sure you've heard this, the leading term, but it's also referred to as the dominant term. And the reason is, if you compare the magnitudes of the three terms in this polynomial, so let's look at the three terms. You have a constant. Well, that constant doesn't change no matter how big x is, so its magnitude is also constant. Here you have a linear term, right? You just have an x term, right? And then here you have a quadratic term, an x squared. So as x gets really, really big, and when we say big, we don't mean 20 or 100. We're talking like tens of billions and trillions and so forth, and even that's not really big. But when you take a really big number and you square it, it is going to be significantly larger than just the number itself. So the x squared dominates all the other terms, right? And that's because it's due to the fact that we're only allowing non-negative integers in our as our exponents, right? So using this dominant term approach, what we can say is, even though we have other terms in the polynomial, when we're dealing with the limit at infinity, right, plus or minus infinity of a polynomial, we can just focus entirely on that leading term. So I could say that this limit is the same as this limit. These are not the same function, right? But as x gets very, very large, they will tend to this, they exhibit the same pattern, right? And what is that pattern? Well, here, let's think about it. Your x is getting larger and larger, and it's positive. And then you square it, so it's going to be even bigger, so it will continue to get larger and larger, and then you're multiplying it by a positive constant. So the net result of this is that 2x squared gets bigger and bigger and bigger as x gets bigger and bigger and bigger. So and the result is always positive. So it's a positive quantity that's getting larger and larger and larger. Well, what do we use to indicate that? We indicate that by positive infinity. Or if you don't want to write the plus sign, you could just do infinity. Right? So with polynomials, they're easy to evaluate at plus or minus infinity. You simply have to identify that dominant term. All right. So let's say this is example 1. Let's do another one. So let's now have something that goes to negative infinity, and then let's say we have negative 4x cubed minus 6x squared plus 1000x minus pi. Right? So that's a polynomial, right? You can have numbers like pi as your coefficient, or e, or square roots. You just can't have them in your exponents, right? Well, because it's a limit. Oh, I think I said, if I didn't say it, I apologize. Let's do the limit as x goes to negative infinity, right, of this one, right? So we have one example with the positive and then one with the negative. So because this is a limit at infinity, what we can do is we can ignore all the non-leading terms, and we can focus on that term with the highest power of x. Again, that's the dominant term, right? And the nice thing about polynomials is that they're easy to identify. Just look for the term that is associated with the largest positive power of x, right? So we can say that that limit is equal to this limit, right? And again, I want to point out something key. The function negative 4x cubed minus 6x squared plus 1000x minus pi is not the same as the function negative 4x cubed. It just, I mean, it just isn't. But what we're saying is, when our independent variable is getting very large in a negative way, or even in a positive way, it's the dominant term, that leading term, that affects the behavior of the function, right? So if this were some other limit as x approaches, let's say 2 or 10, this procedure of identifying the dominant term doesn't work. Why? Because we have our limit properties that says if you have an elementary function and x is approaching a number, you're able to plug in that number and get provided that number is in the domain, right? And get the limit, right? So in this case, let's take a look at what's going on. So I'm going to write something in quotes because it's not really a number, but it's really just a concept. So I have -4 and then times negative infinity cubed. Right? That's essentially what it boils down to. So it's almost like we're going to try to do arithmetic with infinity. And in general, the laws of algebra don't always hold nicely for infinity. But it turns out if you're simply just doing powers like positive powers and multiplying by constants, those rules do follow suit, right? So what do we mean? Well, if we take a large negative number and cube it, we are going to get another large negative number, right? So this would be -4 times. So essentially simplifying this gives me another large negative number. And then I have a large negative number multiplied by a negative constant. So those two negatives make it positive. So the end result of this is that this function, this -4x cubed minus 6x squared plus 1000x minus pi, that function approaches positive infinity as x approaches negative infinity. Right? Leading terms, they make your work relatively simple with polynomials. All right. Now, the next class of functions is it's built from polynomials, and these are called rational functions, or sometimes just abbreviated the rationals, right? And what is it? Well, a rational function is any function of this form, p of x over q of x, where p and q are polynomials. Right, so where p of x and q of x are polynomials. Right? So in general, if you take two polynomials and divide them, you won't get another polynomial. There are some special cases when you will, but in general, if you take a quadratic and divide it by a cubic polynomial, you're not going to get another polynomial. So that's why they're given a different name, right? So it's almost like you're building a fraction, but instead of having numbers in the numerator and denominator, we now specifically have polynomials, right? And it turns out there are some interesting properties, useful properties that will make evaluating these functions with limits at infinity relatively straightforward. Now, there's some special cases of these that are useful. So I'm going to start with the really simple ones. And here, let's say I want to find the limit as x goes to infinity of 1 over x, right? This is a rational function. In the numerator, you have a constant polynomial, and then in the denominator, you have the linear polynomial x, right? So this is rational, and then we have to ask ourselves, well, what is going to happen to 1 over x, this fraction, as x, which is in the denominator, gets very, very large, right? So the numerator stays constant, but the denominator gets very, very large. Well, what's going to happen to the overall fraction? Well, it's essentially this. And again, I'm going to put this in quotes because we don't really, again, what I'm trying to do, let me write that more clearly. What I'm trying to do is essentially establish some algebraic conventions, like things that we will hold to be true, even though they're typically not stated as like properties, right? So, what is 1 over infinity? Well, if you remember, 1 over is where you're taking the reciprocal. So if you take the reciprocal of something very, very large, you're going to get something very, very small. And as that thing continues to get larger and larger, the reciprocal will in turn get smaller and smaller. And in this case, 1 over infinity is said to converge or approach 0, right? So it gets very, very small, right? So something to think in mind. For us, we're considering 0, to be an infinitesimally small object. So infinitely small. And on the other hand, we're taking infinity to be infinitely large, right? So if you take, again, the convention is if you take the reciprocal of something infinitely large, you're going to get something infinitely small. And the converse is true. If you take the reciprocal of something very small, you're going to get something very large, right? So that's a useful convention. Now, let's extend this idea a little bit more with another example, and then we will look at some more complicated rational ones and essentially utilize the conventions that I'm introducing here in examples 1 and 2. All right. So for n, which is let's say positive integer, so 1, 2, 3, 4, etc. Right. What happens if we take the limit as x approaches infinity of 1 over x to the n, right? So instead of just having, x to the first power, what if you had x to some other positive integer power, like a square or a cube or a fourth, etc.? Well, so let's see what it's saying. It's again, we're trying to say what is 1 over infinity to the nth power. Well, if your n is a positive integer, remember what we said earlier with polynomials is that if you have like infinity, squared or cubed, it's even bigger. Well, that's what's going to happen here. Right? So this denominator is actually bigger than this denominator. Therefore, this reciprocal is even smaller than this one, right? In terms of like how quickly will this reciprocal get very small. But the idea is 1 over infinity to the nth power is also 0. So this function, as x gets very, very large, it approaches this quantity that's infinitely many, or infinitely small, right? Okay, so keep those two in mind, and then let's take a look at, so we're going to do 3 more examples of these, and in fact what I'm going to do is just kind of have them side by side in this line. So example 3, we'll have the limit as x approaches infinity of negative 2x squared minus 3x plus 1 over 6x squared plus 10x minus 9. And then let's look at example 4 will be the limit as x approaches, let's say negative infinity now, of 3x plus 5 over, say, 4x cubed minus 1, right? And then our fifth one, the limit as x approaches, let's go back to positive infinity this time, and what if we have x squared minus x minus 1 over 100x plus 9. All right? So let's look at these. These are all rational functions. Notice all I did was I took different polynomials and divided them, and that's how you form rational functions. The trick in all of these, in these rational ones, is to, now there are different approaches, right? And I'm going to show you two approaches. The first formal approach is, since the numerator and the denominators are polynomials, they would each have a highest power of x. So what you would do is look in the numerator and look in the denominator, pick out the largest power of x overall, and divide each term by that power of x. So what I'm going to do here, the trick, again dividing by that highest power of x, we're going to divide each term by, in this case, x squared. Right? That's the largest power of x in the top and in the bottom. Divide each term by x squared. Now there's 6 terms here, right? So it's going to look like this. So this limit becomes, so when I divide the first term by x squared, the x squared goes away, so I'm left with -2. And then if I divide 3x by x squared, I'll have 3 over x. If I divide 1 by x squared, I will have 1 over x squared. So that's what the top looks like when I divide it through by divide it by x squared. And then let's do the same at the bottom. So dividing the 6x squared by x squared leaves a constant 6. Dividing the 10x by x squared leaves a 10 over x. And then finally, bring down the minus and divide the 9 by x squared leaves 9 over x squared. Let me scroll down a little more. And now, when we use our limit properties, if we take the limit, so I'm gonna write down the expression and then that's obtained by taking the limit of each of the terms. So when I take the limit as x goes to infinity of this constant, our limit property says the constant stays the same. And now, if I look at the 3 over x, as x gets very, very large, well, we just said that, again, the numerator is a constant, but the denominator is getting very, very large, like huge. So this particular fraction approaches 0. And similarly here, this is where we have an x raised to a positive integer in the denominator. So this denominator again is getting very, very large. So when I take 1 and divide it by that very large quantity, I get something very, very small, something infinitely small. Oh, I said infinitely and then I wrote infinity. No, that's 0. And then the similar pattern happens in the denominator. So you'll have 6, you'll have a 0, and then you'll have a 0 there, right? So as x gets very, very large, because we've rewritten these in that special case where you have like a constant over some positive integer power of x, then essentially all of these terms, as x gets very, very large, all of these approach 0. So we're left with -2 in the numerator, 6 in the denominator, for a limit of -1/3. And now remember what we said previously is that when a limit at infinity exists, meaning we get a specific number, then it means that this function has a horizontal asymptote at y equals 1/3. So in fact, let's write that down. So this implies a horizontal asymptote at y equals -1/3. All right. Well, let's see if what happens if we apply the same procedure here for the other two. All right. So let me kind of break this up. So here, the highest power of x overall is x cubed. So I'm going to divide everything by x cubed. So we have the limit as x goes to negative infinity. Dividing this by x cubed leaves 3 over x squared because we reduced the x over x cubed. And then here we have 5 over x cubed, right? And then in the bottom, the 4x cubed divided by x cubed is just 4. And then minus 1 divided by x cubed, that's just 1 over x cubed, right? So these can't be reduced anymore. These, we were able to reduce them, right? But guess what? Now these all fall into that basic property where we have a constant divided by some positive integer power of x. So everything that I'm circling here is going to approach 0 as x gets very, very large, right? So these all approach 0. So what are we left with? Well, now we end up with a 0 in the numerator, but then a 4 in the denominator. And 0 divided by 4 is equal to 0, right? So this means that this rational function has a limit at negative infinity of 0, which then implies that this function has a horizontal asymptote at y equals 0. So the line y equals 0, which you might recognize right away as your x-axis, right, is a horizontal asymptote. All right, good. So seemingly a pretty straightforward process. Hopefully you think so, right? So let's take a look at this. We're going to divide through by the highest power of x everywhere. Well, what is that power? Well, that power is x squared. So I have to divide all of those by x squared. So we have the limit as x goes to infinity. Divide this by x squared, it's 1. Dividing x by x squared leaves 1 over x. And then dividing 1 by x squared is 1 over x squared. And then that's all over. Dividing 100x by x squared gives us 100 over x. And then dividing 9 by x squared gives us 9 over x squared. And again, notice what we're left with. We're left with those familiar forms of a constant divided by positive integer powers of x. And everything here will approach 0. But now it's a little strange because what do we have? Right? Now, so clearly the bottom is positive, right? So we're approaching 0 from the plus side in the bottom. And then in the top, it's approaching 1, right? Because it's 1 minus 0. So we have this. So I'm going to write it like this. And then with the understanding that at the bottom, everything here is positive. X is positive. We're squaring the x, and then we're adding those two together. So this would be 0 plus. And we know what that means. That's actually one of our infinite limits. And like you have a non-zero constant divided by something that's getting very, very small. So that means in this case, the fraction is getting very, very large, but in a positive way. So in this case, this rational function does not approach a number. It doesn't approach a number like negative 1/3 or 0. In fact, it approaches positive infinity. So in fact, this function has an infinite limit at infinity, right? So this is a nice play on words, but it's an infinite limit because it goes off to either plus or minus infinity, and that's our definition of an infinite limit. But that occurs as x goes to infinity. So at infinity. Right? right? So these three, and it turns out that these three examples illustrate the only three possibilities for rational functions. Either the rational function is going to approach a non-zero constant, or it's going to approach zero, or it's going to approach plus or minus infinity, meaning it has an infinite limit. Now, another trick that is sometimes taught is that you can identify these three cases simply by looking at the leading terms. So here, the dominant terms, the dominant term in the numerator and in the denominator have the same degree, which is why they got canceled out here. All the other terms go to zero. So you're essentially left with the leading coefficient in the numerator divided by the leading coefficient in the denominator, right? So whenever your degrees are exactly the same, it's going to be this first case where they approach a non-zero number. Look at what happens here in this one. The degree at the top is less than the degree at the bottom. So what happens is when you divide by this highest power here, you're going to be left with a constant here, but then you're going to be left with terms that approach zero as x gets really, really large in a positive or negative way. And that's why you end up with a zero in the numerator, but a non-zero in the denominator, which reduces to zero. And then over here, it's flipped, right? So in this particular case, the degree in the numerator is bigger than the degree in the denominator. Hence, you could say that this term dominates the whole thing. That just makes the whole fraction get larger and larger and larger, right? For that reason, and what I'll do, I will just illustrate it with one of the examples here, and then we will end this video. Let's say I redid my first example, so I'm going to rewrite it. So here's kind of an alternative approach. So let's say you have the limit as x goes to infinity, and we have the negative 2x squared minus 3x plus 1 over 6x squared plus 10x minus 9. What we can do is, since these are both polynomials, let's use just the dominant terms in each of them. So this is the term that dominates the numerator. This is the term that dominates the denominator. So therefore, based on what we did with polynomials, that limit, my original limit of this rational function, is the same as this limit, right? Again, we can ignore the non-leading terms, but we can only do this when it's a limit at plus or minus infinity. It's just that these terms get so big that you can ignore these lesser terms, right? You know, you're kind of insulting them, but unfortunately, yeah, these are lesser terms as far as x getting very, very large. So the limit of this rational function is the same as the limit of this rational function. Again, I want to emphasize that the functions themselves are different. What we're saying in a limiting sense is that they approach the same number, or they have the same property as x goes to positive infinity. But now here, since you have a monomial in the numerator and a monomial in the denominator, reduce this to its lowest terms, and look at what we've got. The x squared completely goes away, and you have your negative 2 over 6, which we know reduces to negative 1/3. And that's what we got here. That's what we got here. Right? So the previous method where you divide through by the highest power of x, that's kind of the formal way of showing your work. This way is still valid. It's just that you're using a slightly different concept. You're applying the properties of polynomials when x goes to plus or minus infinity, but you're applying it to what's going on in the numerator and what's going on in the denominator. Right? But algebraically, it works out to be the same. Right? So we'll continue our look at the different elementary functions and how we compute their limits at infinity in the next video.